world around us is constantly changing, and in mathematics, we have a precise way to measure that change. This process is called differentiation. As it's heard, differentiation is a tool in calculus used to find a derivative of a function. What does a derivative tell us? Simply put, it measures how fast a quantity is changing. This is the rate of change, or when looking at the graph, the exact slope of a curve at any given point. Consider a classic example. The function y equal to x power of 2. The derivative dy over dx is 2x. The simple result is profound. It means the slope of the curve is not constant, but continuously changes depending on the value of x. The steeper the curve, the larger the derivative. Now, what is the technique of differentiation? First, constant function. The constant is the main intention. For example, y equal to c, which is c is a constant. Second, power function. The power of the constant is the main intention. For example, y equal to x power of n. This n is any real number. Third, polynomial function. They include variable rates to non-negative whole number power. Each term is formed by multiplying a constant with power of the variable. Next, we have sum and different rules. Differentiate a sum or difference of function, you differentiate each term separately. For example, y equal to fx equal to u x plus minus vx. Next, product rule. When two functions are multiplied. And the last, quotient rule. When one function is divided by another. Differentiation of trigonometric function. The process of finding the derivative of trigonometric function is known as the differentiation of trigonometric function. In other words, the differentiation of trigonometric function is finding the rate of change of the function with respect to the variable. The 6 trigonometric functions have differentiation formula that can be used in various application problems of the derivative. The 6 basic trigonometric functions include the following: sine, cosine, tangent, cotangent, secant, and cosecant. In this slide, we will find the derivative of the trigonometric function and their proof. So, what is the derivative of exponential function? The derivative of exponential function fx equal to ax, which is a more than 0, is the product of exponential function ax and natural log of a, that is fx equal to ax ln a. Mathematically, the derivative of exponential function is written as dAx over dx equal to ax prime equal to ax ln a. The derivative of exponential function can be derived using the first principle of differentiation using the formula of limit. The graph of derivative of exponential function change direction when a more than 1 and when a less than 1. Lastly, we're gonna see logarithmic function. Derivative of logarithmic function are mainly based on the chain rule. However, we can generalize it for any differentiable function with logarithmic function. The differentiation of log is only under the base e, but we can differentiate it under other bases too. For example, derivative of ln x, that we can prove this using first principle, and derivative of log ax. We will use base changing formula to change the base of the logarithmic to e.
Now that we have looked at all the techniques of differentiation, let's do some exercise to understand more about differentiation. Shall we? Let's go! Now, let's look at these two questions. Find the dy dx for the following function. For the first one, the equation is y equal to e to the power of negative 2x times 3x plus 1. From this equation, we need to use the product rule. So, let e to the power of negative 2x become u, and from this, you need to use the chain rule to get the u prime. So, for the u prime, e to the power of negative 2x times dy dx of negative 2x. So, you need to multiply the e to the power of negative 2x times negative 2. So, you get negative 2 e to the power of negative 2x as the u prime. For the v, let 3x plus 1 become the v. So the v prime is 3. Next, apply the product rule, which is dy dx equal to u prime times v plus u times v prime. Then, insert all the information that we have gathered into the formula, which will be dy over dx equal to negative 2 e to the power of negative 2x times 3x plus 1 plus e to the power of negative 2x times 3. So, first, we need to expand the negative 2 inside the 3x plus 1 bracket. So, it will be e to the power of negative 2x times negative 6x minus 2 plus 3e to the power of negative 2x. From this, we need to separate the e to the power of negative 2x from the others. So, it will be e to the power of negative 2x times negative 6x minus 2 plus 3. Then, just solve what's in the bracket and you will get the final answer e to the power of negative 2x times negative 6x plus 1. To make it even more simple to understand, turn it into e to the power of negative 2x times 1 minus 6x. Pretty easy, right? Now, let's look at the next question. The equation that we need to solve is y equal to square root x plus sine 3x. From this equation, we need to turn the square root into the power of 1 over 2. So it will become x to the power of 1 over 2 plus sine 3x. So first, let's start differentiating the x to the power of 1 over 2. The rule that applies for this is the power rule. So it will become dy over dx x to the power of 1 over 2 equal to 1 over 2 x to the power of 1 over 2 minus 1. Then, you will get 1 over 2 x to the power of negative 1 over 2. From this, we need to change the x to the power of negative 1 over 2 into 1 over square root x. Then, we just have to multiply the 1 over 2 times 1 over square root x. Then, the final dy dx of x to the power of 1 over 2 is 1 over 2 square root x. Next, differentiate the sine 3x. So, the equation will be dy over dx sine 3x equal to cos 3x times the dy dx of 3x. From this, we actually use the chain rule. Then, it will become cos 3x times 3. So the final dy dx of sine 3x is 3 cos 3x. Then the last step is to combine the derivative of both terms. So the final answer will be dy over dx equals to 1 over 2 square root x plus 3 cos 3x. It's easy, right?
So for question 3, the question asks us to find dy over dx for the given function by using implicit differentiation. So step 1, we must differentiate both sides of the implicit function with respect to x. And the equation will be d over dx times e to the power of 2y plus 2x equals to d over dx times y cubed plus cos 4x. After that, we need to expand them and differentiate each of them, and we will get 2 dy over dx e to the power of 2y plus 2 equals to 3y square dy over dx minus 4 sine 4x. And step 2, we need to factor out dy over dx on one side of equation. So here, I bring the dy over dx to the left hand side, and we will get dy over dx times 2e to the power of 2y minus 3y squared equals to negative 4 sine 4x minus 2. And step 3, solve for dy over dx. So, the final answer, we will get dy over dx equals to negative 4 sine 4x minus 2 over 2e to the power of 2y minus 3y squared.
So now let's move on to question number 4. As we can see in the question, it asks us to use linear approximation to estimate the value of 1 over the cube root of 124.99 plus the cube root of 124.99 all squared. Now, let me show you guys how to solve this problem. Okay, first, we will identify the fx as it shows in the slide. I rewrite the function and convert the cube roots to powers. Example, fx equals to x power negative 1 over 3 plus x power 2 over 3. And then, I will find the derivative. I differentiate it using the power rule. f prime x equals to negative 1 over 3x power negative 4 over 3 plus 2 over 3x power negative 1 over 3. After that, I choose a convenient value, which is I determine the values of x and the estimate value. I choose 125 because it is a perfect cube and it is very close to 124.99. The cube root of 125, it will equals to solid 5. Then I determine the values of f estimated value and f prime estimated value inside the equation. For f125, for f prime 125, it's approximately equals to negative 15 over 28,127. Lastly, I apply linear approximation formula, which is fx approximately to f estimated value plus f prime estimated value times with delta x. Then we substitute it. F 124.99 approximately 25.2 plus negative 15 over 28,127 times with negative 0.01, and the final answer we'll get is 25.200.
We begin the journey by asking how do we measure change not over a long interval but in a single further instant. The answer lies in differentiation. Remember, derivative fx is simply the instantaneous rate of change of a function. Geometrically, it is a precise slope of the tangent line at any given point on a curve. Its determinacy if a change will and quantified in movement with absolute mathematical precision. Through the power rule, the product rule, the cohesion rule, and the indefensible chain rule, we have mastered the technique to find the derivative of nearly any complex function. These rules are not abstract exercises. They are the fundamental tools that unlock the analysis of dynamic system. The true power of derivation is since it is in application, it allows us to achieve optimization, to systematically find the precise maximum profit for a business or the minimum material needed for a construction project simply by setting the derivation to zero. It gives us velocity and acceleration in physics, and in economy, it provides the powerful insight of marginal analysis, the change caused by just one extra unit. Differentiation is more than just a chapter in a textbook. It is the mathematical bridge between static number and dynamic process of the real world. It is the key to understanding how things change when they are here at their best and where they are going. Mastering differentiation is mastering the analysis of change itself. Thank you.